Okay, I put a presentation for you guys together that if I was going to present to the science committee or the president himself, because this is such an important issue and it's such an enormous expenditure of the public treasury that there can be no failures. A mission to Mars requires almost 100% surety that you'll get there. So what you're going to learn here is what our politicians probably don't know. Some of them do. Dana Rohrabacher does. He used to be the subcommittee chairman. What you're going to learn is everything about Mars. We know everything about Mars. The only thing we don't know is where some of the minerals are and where some of the processes are, but as far as getting there, what's on the surface, what's going on there, we know. And I'm going to prepare this like a technical readiness level analysis meeting, as if I was back at the space station program, talking to one of the heads of the program. And there it is. TRL levels is what we talk about in the industry. So my name is August Dunning, and I work at Caltech. I'm in Bill Johnson's group. It's the bulk metallic glass architecture group, and we produce these interesting alloys of niobium and iridium and cobalt, and they have thermoplastic characteristics so they can be formed into a shape at a certain temperature and be used to create, for instance, the hull of a spacecraft. And in layers of these things, they're very effective, and I'll show you that. So when it comes to propulsion, the TRL level is about 10. We got the big boosters. We've got the ability to get out there. We launch all the time. Logistics and support, yeah, we got mission control. We've got every place. We've got Goldstone. We got all the tracking. That's all there. Environmental support, sure. We can do a on orbit for years on end atmosphere, shirt sleeve environment. No problems there. Habitat, subsurface. And as you'll see in this presentation, it will have to be subsurface. And we don't know how to do a lot of this stuff. We don't have the machines to do it on the moon, for instance, where we're going to probably learn first. Solar radiation shielding. Joan talked extensively about this today. And that's one of the bigger issues. We have a lot of the materials that can protect us from almost everything coming at us from the sun. Okay? But galactic cosmic rays is a completely other issue. So there's nothing like space flight. When you get into orbit on a Soyuz and you're floating around there with a couple of smelly guys and you're just excited as hell, it's really incredible. And you're stuffed in there, see all the packing material, that's all their supplies and stuff. They pack the thing tight. All they can basically see is the screens in front of their face. But it's fantastic. We're very good at locating the space station and rendezvousing and hooking up and attaching, and the probes hit and you're on there and you're attached fixed and you open up the door and you climb in. It's easy. But we're a spacefaring nation now. We're a spacefaring race. We're never going to go back. We're never going to stop doing this. We do it every day. This is an EVA on the space station, on the Unity module. And you can see that it's really amazing. It's really clean up there, except for a lot of stuff flying around really fast. But there's the NASA Unity, which is the ISS safe haven, but there's nothing like the view. We have a new spacecraft called the Orion, bigger than the Apollo. We've gone back to a bladed heat shield, so you just come in with friction and you don't have to worry about blowing up on the way up there now. We have these modules, service modules that can take us out to the moon and further. Elon Musk is getting involved. Elon has a very, very ambitious project going on. ESA is going to fly an Orion around the moon. But there's the problem with the moon. There is some shielding in the tail, but for the most part, the moon's orbit is outside the geomagnetic field of the Earth. So it's not protected. And the real problem is this. It's only 200 miles up is where we are protected. So space stations, some of the satellite missions and stuff, you got some protection. But there's really no protection up there above 200 miles because the galactic rays, the solar energetic particles, it's really, really a mess in space. And we know because a lot of the Apollo astronauts have heart problems caused by space exploration on the moon. So when we look out past the moon to Mars, or even further, we need to solve this problem. Hollywood makes us think that it's easy. We'll have balloons floating around, people run around in spacesuits on the surface, it'll be fun. But I'm here to tell you that it's a cold, dark, no vegetation, poisonous atmosphere. You can't breathe it. You have to be in a spaceship or a spacesuit because it's being on Earth at 25 miles up. It's only 1 millibar of pressure. It's a very dangerous, dangerous mission. I can't stress danger enough. It's a vastly different level of difficulty. Going to the moon was quite an achievement. It's only three days away. This is 6 months away. So let's understand the radiation risk during interplanetary human space exploration, because that's really what we're talking about here. That's the real Mars mission challenge. These storms that blow off the sun impact the Martian environment in ways that it does not impact Earth. Let's talk about deep space radiation. Here's all the different types of particles. We've got solar wind, full of auroral electrons and trapped protons and trapped electrons and in the inner zones. And in particular, we're worried about the solar storm protons, the solar flare protons, and the galactic rays. Now notice that the solar storm protons aren't traveling as fast as the solar flare protons, and we've shown this, that these flares, they hit us in minutes, traveling along our magnetic field lines to the Earth. CMEs and mass ejections of protons take a little while longer, okay? Because we're existing in this all the time. The sun is constantly off-gassing hydrogen and atoms and wind. This is just the general solar wind. And when it hits the Earth, and a storm does hit the Earth, the magnetic field compresses in the solar direction. And it tries to repel back that onslaught of charged particles. It has for 4.5 billion years. That's why we're here. Carrington event in 1859 is where it actually broke the field. Minus 1900 nanotesla event that busted through the magnetic field and ignited all of the telegraph lines on Earth. Because these are long waves, long lines, then it means the electrons had to be inducted at the surface and cause all these fires in cities and stuff. Because the Earth has this protective field, it protects us over geologic time from this damage. But that's Mars's field. That's us. That's Mars. We're not protected. Now, we also have the Mars Atmosphere and Volatile Emissions message, which is the MAVEN spacecraft. MAVEN's gone out there and it's measured the solar wind density compressions at Earth and at MAVEN out of Mars, and sure enough, they don't lose any power as they get out there. And they've done the energetic particle fluxes, how many, when they parse out, no reduction in intensity there either. And here's something you don't generally see. This is the Enlil all the way out to Pluto. And you can see these solar storms that left the sun long ago are way out in the outer planets. And notice in the right panel at the top, when a solar wave hits the New Horizons spacecraft, and that's when we lost communication, right before it got to Pluto. We thought we lost the spacecraft after all those years. Fortunately, it flipped back on. So we have this electromagnetic soup, and then this, radiation from outside our star system, galactic cosmic rays from supernova and other events. The physiological effects of radiation exposure. Because astronauts are in the bubble. They're in their little spacesuits, well protected outside. They're in below 200 miles up, so they're well protected by our field. There's still things that don't hurt them, but galactic cosmic rays, when they come in, hit another atom, which busts that atom up, which busts more atoms up, to this huge spray is coming down to the surface and actually penetrates the surface. Now that we know how the secondary radiation evolution happens during a galactic ray impact, isn't that a good theory for the evolution of genetic mutations over time on Earth? If this has been hitting us since we began, then we're getting mutations in cellular tissues and maybe even genetic tissues every day. And that's really a source of evolution, not just natural selection, that's part of it. But there could be a radiation emission. And in space, that's the problem. When these particles pass through the spacecraft hull, they create secondary particles that go through the human being. And the astronauts all talk about this. You get the flash. You get a flash little line when the galactic ray hits your retina. But if it's hitting your retina, it's hitting everything else too. Okay? So it's really an interesting issue. And on orbit, we have some ways to protect our astronauts during flares. These high-density polyethylene shields and Lexan and Lucite and stuff, and they go into these Lucite boxes because heavily hydrogenated carbon-chained materials tend to absorb galactic rays and radiation better. But it's the effects you have to worry about. You know, we know very well the effects of radiation from all our years working with nuclear weapons. But what we're really concerned about is the level from about 1,000 millisieverts up to about 5,000. Because during space flight, you're exposed to a lot of radiation. If you get to 2,000, you get acute radiation sickness, which is vomiting, nausea, fatigue, cloudy thoughts. You can't operate. That's not good for an astronaut. And that's the problem. Here are the typical dose equivalents in millisieverts for your annual cosmic radiation here at the sea level and U.S. average abdominal CT scans, DoD radiation worker annuals in the nuclear plants, 6 months on the ISS in yellow, and then 180 days to Mars, 500 days on the surface, 180 days to get back. You're talking an 860-day radiation exposure. That's about 1,500 millisieverts, and that's in that range between higher chance of cancer, acute radiation sickness, and incapacity to crew, and that doesn't count solar flares or cosmic rays or solar proton storms. The suits offer no protection. You get neurobehavioral decrements in anxiety, fatigue, and performance, cataract formation, damage to the quiescent neural stem cells in the hippocampus, increased skin cancers, degenerative circulatory system damage, prodromal effects such as nausea and vomiting, skin burns, changes to bone and muscle and so forth because protons kill bone marrow. If you get hit by a big enough solar storm of protons and it kills all your bone marrow, you don't make any red blood cells. If you don't make any red blood cells, you're dead in 2 weeks because your body's constantly replacing them. And here's why it's dangerous. X-rays can damage the nucleotides. Heavy ions and galactic rays can bust it apart. And we've already seen this in astronaut post-flight chromosome damage, where we've got busted chromosomes, violation insertions, and a lot of the astronauts, 39 of the former astronauts, suffer from cataracts from space travel. Let's compare Mars to Earth. Mars is about half the size of Earth. It's about 4.5 light minutes away, but 180 days by vehicle. They have dramatically different interactions with the solar wind. Mars, because it's so exposed, is hit by solar wind, energetic ultraviolet, solar energetic particles, coronal mass ejections. There's very little protection. You get pickup ions flying off the surface of the planet up into the air. They get blown up with the solar wind. You get auroras on the planet. You get magnetic fields lifting, because these fields are not exactly aligned in these magnetic bubbles. They're all over the place. And we have a thermal tide on Mars. It's like a standing heat wave. As the ground heats up on the dawn side and going towards noon, it expands the atmosphere out. And then as it goes away and it starts cooling, it contracts it down to a complete condensation of gases in the atmosphere at night. And just like on Earth, these big updrafts cause big downdrafts. So as the wave goes over Olympus Mons and builds up, the downdrafts from the crater go down. The heat wave drives the updrafts up. And on RCA Mons, we see lots of dust devils, great big dust devils. So big, in fact, that they get up past the troposphere and get blown off in the late afternoon, or blow off as plumes during the day or afternoons. And the atmosphere is just exposed to solar wind. You can just see how it immediately over the days, just bang, 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 is affected. So what this means is during the day, when the atmosphere expands, the pressure goes down, the blue line. But at the same time, the thinner atmosphere allows more radiation to come in, so your radiation exposure goes up during the day. So you can't work out during the day because the radiation is too high. You can't work at night because it's too cold. What a charming place. It has about the same inclination angle right now as us, so it has seasons. The northern winter is actually the southern summer, but it's a little more eccentric than our planet. And because of that, it lifts a lot of dust, and you have these 6-month, 8-month-long dust storms. And a lot of the dust is paramagnetic. This is the UV sensor, and you can see dust building up in the magnets around the sensor heads. We know a great deal about this planet. Every day, or every Thursday, you get a weekly dump from MSSS Marci, M-A-R-C-I. This is the Maitland Science Center evaluation of the Mars Reconnaissance Orbiter scans, and it gives you the weather day by day, gives you a weather report of the past week, and you can see what's happening on Mars. No time in history have we had this much resolution on any planet daily. We've been there a lot. We have some 42 missions that have gone up so far. The red X's are the failures. We've failed many more times than we succeeded. The Mariner missions in 64 to 71 were flyby missions. These missions took snapshots of the planet that we thought was lines and canals. Turns out it's a lot of craters, a lot of dust storms and weather, ice on the polar caps. The first color photographs came back by these things, and the indisputable evidence of water that floated sometime in the past on Mars. So we planned a mission up to the northern basin, which is where we expect an old ocean used to be, Viking 1 and Viking 2, and later the Phoenix. The Viking missions in 1975 were the first successful landings on Mars by any nation. Viking 1 landed in Chrysaor Planitia, broadcast back the first color pictures of Mars from one of our landers. Viking 2 landed in Utopia Planitia, up north of Elysium Mons, and in the morning of September 9th, broadcast back snow on the ground. So did Viking 1. Phobos 2 mission, this is the Soviet Union mission, it was 2 landers, Phobos 1 and 2. Phobos 1 was lost on the way out there from a bad command. It was a very, very hardy little workhorse. It was a very ambitious mission. It was going to land a lander on the moon Phobos. And it got there successfully in 1988. And it took fantastic pictures of the Martian terrain. It also discovered that Mars's interaction with the solar wind is very much different than what we thought it might be. There is a bow shock at the beginning, much like ours, but different, because it's so close to the planet. And next to that plasma boundary layer, there's an enormous interaction with the gases of the atmosphere and the solar wind. In 1989, we arrived. In February of 89, it showed the general field structure. But then by March 21st, 89, had this huge spike in the electrical current predictions for the bow shock. And unfortunately, it lands top of the solar cycle. And sure enough, on March the 6th and 9th, an X-15 flare, and on March 9, a huge coronal mass ejection blasted out from the sun, caused huge auroras on Earth, seen all the way to Texas and Cuba, took out the Canadian power grid, and left the sun, the first of the X-flare, at 208 million miles an hour. That's 1.93 days to Mars. It went out, it hit Mars, then came the coronal mass ejection, which hit the Earth, and then hit Mars. This spacecraft was bombarded with high-energy protons and radiation from these 2 flares in the CMA. Now, on March 25th, 1989, Phobos 2 was around Mars in about an 8-hour orbit, which matched the orbital period of Phobos, so the Phobos would fly by it, and when it came by, it would throw a lander down on it. And here's how it worked. At 9:22, it was inside the Mars tail sheath. At 9:42, it was entering this huge zone of pickup ions and interactions and solar energy particles. 10:02 was leaving that, and at 10:22, it was now completely in a different polarity. So it started around here, got to that, and look at camera 3. It's gone after this. At 188 kilometers, the closest approach, that camera was lost. Camera 3 was lost, camera 2 was lost, and soon camera 1 was lost because the spacecraft was lost. Because of these regions of high energetic particles on subsystems that had already failed and were working on backup systems, and we lost the spacecraft, which means that's the first spacecraft that was destroyed by a solar event. Go Soviet Union. Anyway, and here's how it works. The magnetic field has this production of flow of gases up out of the atmosphere. It interacts with the solar protons, forming a bow shock. So we have an induced magnetic field on Mars, not an inherent one. The Global Surveyor mission in 2003 arrived in an aerobraking maneuver which capitalized on saving fuel by going into the atmosphere only briefly to slow it down. It was a braking operation. But when it went in there, it started detecting these very interesting magnetic occurrences that turns out are buried in the surface of Mars. They're not deep. They're only 12 miles down, about 24 kilometers. But they're concentrated in a certain area of the southern hemisphere, and they're very strong at 1,500 nanoteslas. But notice this. They're also minus and positive. That means the fields are going this way, and they're coming out this way all over the planet in that area. And they've got 600 nanoteslas at 200 kilometers up. And the electron reflectometry shows that that's exactly what's happening. Electrons being repelled from electrically minus regions. And we now have mapped it very well. The best place to land, in my estimation, is about 55 degrees south latitude, 180 degrees east longitude. If I was making emission planning, that's the place I'd go because that's probably the safest place as far as any kind of protection on Mars. We also know the radioactive decay cycle for rocks. We know that, we had a lot of things going on there that was heating up the core, and the core was making these volcanic behaviors and so forth. And there was lots and lots of volcanoes, as we've seen, 3 or 4 big ones in the Tharsis Mons, and they were pumping gas into the atmosphere. Now they're just, artifacts. But what's interesting is this map, because if these are plumes from these magnetic fields, some kind of plume of the core, the former magnetic core, you'd expect to find a lot of gravity there too because of their density, but you don't. Tharsis volcanoes, plenty, but not where you find the fields. Interesting, because we had a crater hit Chicxulub, Yucatan, 60 million years ago, and what happened was a 6-mile diameter rock hit it and left a crater with a magnetic signature, which in my last year's presentation suggests the idea that something happened during the late bombardment period of a very strong material and very magnetically stable material over geologic time, hitting and penetrating, being trapped inside the surface of Mars. Because that's what Mars looks like now in a cartoon form. These bumpy, lumpy fields, these little wispy fields of protection here and there on Mars. What's beneath the surface there? Because they're also on the moon. These same magnetic anomalies exist on the moon. Our magnetic field allows the auroras to form these huge arcs over the poles because of the field lines. But because there is no field lines on Mars, the solar field lines wrap around the Mars and then has an interaction with the solar electrons. And that's what Mars's auroras look like. Also, we have this magnetic field effect on the surface affecting the interaction with the solar wind on the forward side. We've tracked that at Enlil's at Mars, and it tracks the incoming solar particles. In this particular red line, at that point on February the 4th, it's 2.2 particles per cubic centimeter at 5100 degrees Kelvin, traveling at 500 kilometers per second. When it hits the magnetic field pressure, it actually backs up a little bit by -2 kilometers per second and deflects by 1 kilometer per second because we know the field pressure inside that zone. The MGS mission recorded multiple solar storms in October of 2003. These are the October storms, they're Halloween storms. And these were all Mars directed, and particularly that one, and that one. And coming up, that one. Here's what it looked like on the sun. Bam. 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 And coming up, wait for it. Wham. And on Mars, the electron flux was so dense and so intense. And you can see the red arrows are where the flare left the sun. The lines are where the flare hit the planet. And it actually penetrated the surface, much like the Carrington event. So the auroras and the solar wind immediately hit the surface. And in fact, that particular event blew off more atmosphere than they were expecting. And they think that this might have been an ancient, way that the atmosphere was blown up by solar wind. I do too. Phoenix mission, north of 60 degrees north up in Vastitas Borealis. And this mission was aggressive because they thought, okay, if there's water there, we should be able to dig in and maybe find some salts. If these are salty seeds that had any kind of life in it, we could find some salt. And what they did was they landed, they blew the stuff away with their rockets. They thought, eureka, salt. But they didn't notice the water that had condensed on the landing struts. And they then noticed the spectral lines of water in the dig spots. And then they noticed that over a couple of days, the salt was evaporating? No, ice evaporates. And then it gets covered with dust. And it's also happened to the Phoenix. It's covered with dust now too. Mars Science Laboratory, Curiosity. Okay, on the outbound phase, out in cruise phase, a large storm, proton storage, left the sun, missed the Earth, hit the spacecraft, and caused this proton event inside the spacecraft by the RAD device under the heat shield that would have killed every astronaut on board. Or they would have lasted a couple of weeks and then had no blood cells and died from oxygen starvation. On the surface, the rad measurements kept going. That's what it's doing now. And they have heavy ion events from the sun and galactic cosmic rays from outside the solar system. Maven mission started pulling this all together. He goes in and out of the ionosphere. He's been tracking the escapes. Maven predicted that ancient magnetic field collapse may have triggered a loss of the atmosphere. I completely concur. Because there is water on Mars, but where did all the oceans go? We know it was a wet planet. We know it was full of ocean water. It was soaking in this stuff. And it was really muddy too, because all this dust and all this water and no plant life was nothing to hold any soil or build soil. So there's the history. About 1 billion years after the formation of the oceans, suddenly Mars lost its ocean. Mars Reconnaissance Orbiter has done deep penetrating radar and found huge amounts of water subsurface above the base polar ice, covered by dirt again, or soil. Huge glaciers that are concentrated in these regions. So let's look at the loss of the atmosphere and sequestering the planetary water as ice. Early on Mars, it had a magnetic field. It had a very molten core. It was producing a big field. It protected the planet. The volcanoes were pumping gases into the atmosphere. It was forming an ocean where the deep bombardment happened, mostly in the upper part. This was like 2 or 3 meters thick. It's a big, big sea up there. These guys kept gassing up, making atmosphere, until you had this. There's the late Neocean period, about 3.8 billion years ago. Big ocean, lots of weather on Mars, thick atmosphere, everything was fine. During that time period, it was inclined to the sun so that that ocean during the summertime was evaporated heavily, forming a lot of water, which formed a lot of rain, which formed a lot of gullies and valleys. Well, we know that after about 1 billion years, that core cooled off, and iron not in motion doesn't produce an electric field. And we can pretty much time it in the late Hesperian period. And it was during a time period where Mars' rotational axis changes because it doesn't have a big moon like us. So its inclination angle isn't like 24 degrees. It's 58 degrees. It can really flop over. So this, in combination to a eliminated electromagnetic field, caused water to be blown off into the sky and rain down to freeze here as the air pressure went down. And when that happens and you're not protected, the sun just whisks away. It's called sputtering. Mars today is the example of that physical process on planets that lose their electromagnetic field. That's why we worry about this one with its field problems right now. We had ancient streams, ancient groundwater, ancient dunes. What are these lines actually telling us? Because there's a good argument that says now, in June 2012, this Japanese team discovered they're calling the Charlemagne event, which was an event recorded in carbon-14 by a solar storm that ionized nitrogen into carbon-14, taken up in trees, in the tree rings. They analyzed it. They said it was at least 10 times or 20 times greater than the Carrington event, which was 1,900 nanoteslas. So you're talking about minus 19,000 to minus 38,000 nanoteslas? Could it be higher than that? Maybe, because the orange line is the luminosity of the sun. And early on, the sun was a very violent star. Very violent. Lots of storms, lots of stuff hitting the sun, lots of stuff hitting the planets, lots of bombardment. And then about 1 billion years after that, it had calmed down, grown an atmosphere, because it could protect it with a magnetic field that it still had, electromagnetic field. But then, that cooled off. Big solar storm comes, no protection, you blow your atmosphere off. Maybe in a single event, a huge proportion of the atmosphere, to equal out what's left of any gravitational holding of an atmosphere. So what happens here is 300,000 nanotesla storm sputters off 20% of the atmosphere, 3.75 billion years, and over another 200,000 years, you're getting rid of another 40%. So rapidly, you've lost your gravity field and your atmospheric pressure. And when that happens, water can't be on the surface because water boils at lower and lower surface pressure. Up on Mount Everest, it boils at 79 centigrade, not 100 centigrade. So as you lose your atmosphere, water just boils off. Curiously, though, if you'll notice the Earth's environment compared to the Martian environment, and down below, the oxygen curve over 3.5 billion years. When this happened, during the late Neocean, when this event happened to lose Mars's magnetic field, electromagnetic field, the first photosynthetic bacteria were absorbing infrared and creating sulfates on Earth. But after this event, a new bacteria showed up that converted CO2 to oxygen, and the great oxygenation of our atmosphere occurred. Was that a consistent event? Did the same solar storm that hit Mars hit Earth and cause genetic mutation in the algae, which caused them to start processing a different gas? Curious. So now the atmosphere of Mars is about the surface of 22 miles up on Earth, 1 bar pressure. That means that only at certain times of the day and certain temperature ranges can there be any liquid water, and the liquid water seeps out of the side walls of craters and stuff. Because it does get well above freezing on Mars during the day in the summertime. And it gets, so these ices can melt, weep out into the mud. Then the ultraviolet hits it, it evaporates off into gas. It then breaks up in the upper atmosphere and blows off the planet every day like this. There goes your atmosphere and a lot of your water. At night, it's a minus 104 degrees air temperature and minus 140 degrees ground temperature. So all the water condenses on the night side. That's in the atmosphere that hasn't been blown off. And that's how it works. If you'll notice the blue lines, there's a little bit of that blue that's coming back onto the planet at night. And there's some of the blue is being blown off. A lot of the gases are being blown off. So what Mars's hydrological cycle is a semi, not 100% loss from evaporation during the day, because some of it's captured at night. So it's throwing stuff off, it's grabbing a little back, and it's been doing that for billions of years, because there's a lot of ice. So the early mission showed we have an extremely thin, unbreathable carbon dioxide atmosphere, high levels of radiation exposure in orbit, extremely high and low temperatures on the surface. Solar radiation causes weather and H2O vapor evolution. Solar storms directly influence the rate of atmospheric loss. Subsurface magnetic anomalies influence the rate of H2O vapor condensation on the night side seasonally. Mars Global Surveyors show that the solar storm penetrates the atmosphere to the surface, and galactic cosmic rays are constantly bombarding the planet. Boy, sign me up tomorrow. Okay, so the technical readiness level of radiation protection for manned space transfer spacecraft and Mars habitat structures and architecture. Deep space micrometeoroid environment, because this is just as dangerous as the other stuff. We get hit by a lot of stuff. These are the solar panels on the Hubble Space Telescope had to be replaced. These are thermal sheets that have been penetrated by tons and tons of meteoric dust. This is the Stereo A hit by a meteor. So we think, well, okay, we'll just build up big enough sections to protect them from these kind of things and head on out to Mars in these great big spaceships with these huge, bizarre shielding things. I don't know how you launch the thing or assemble it to begin with. Here's the problem. Alpha particles stop by Pfeiffer. Beta particles, which are electrons, positrons and electrons, are stopped by, aluminum plates. Gamma rays and X-rays, well, you got to have a lead or steel. That's why they put the lead graping on during your dentist appointment. Or neutrons, which can be stopped by water. But it's galactic cosmic rays that NASA recognizes is the most important thing to deal with, because we don't have any protection, and they're very, very energetic particles. And this stuff doesn't stop them at all. It's all transparent to them. So we've done shielding experiments. We know the free space environment at Earth at 1 astronomical unit. We know the lunar surface and the Martian surface. We've investigated all these different materials. Aluminum, polyethylene, liquid hydrogens, different thicknesses, and they all basically have the same behavior. Polymeric materials show a decreased absorbed rate, which we talked about, because they have a very high hydrogen content. Lithium-infused polyethylene seems to be about the same absorbed dose as 5% borated polyethylene. But notice the curves. There's no standouts there at all. Carbon fibers, maybe a little more, but not much. So we go to Z-graded materials, just density. And we have to dope them to absorb the neutrons produced by the proton destructions, right? And look at that, though. Can you really think about a spacecraft that's got tons and tons of heavy metal shielding? And we've tested this stuff. Here's the proton source beam exposure. This is in Loma Linda. And we expose them to protons, and we get the results, and sure enough, they're about the same. If you'll notice the dot line rays, there's a little bit of, even the thickest stuff, you're still getting tons of exposure. The best seems to be the lithium and boron infused materials. And the simulation did show that a comparison to aluminum borated polyethylene, lithium doped polyethylene, and neat polyethylene produced less absorbed dose of GCRs than aluminum, and thus are better radiation mitigators. So great, we did it. We'll get borated polyethylene in all the spaceships, line of things, and well, maybe, because it needs to be 3 to 5 meters thick to protect from galactic cosmic rays, which kind of makes it impractical. And this is the chart that shows the problem. If you look at the green line, which is solar energy particles being shielded by hydrogen, you get 100% shielding with about 10 grams per centimeter of liquid hydrogen. Polyethylene, a little thicker, but you can really block all this stuff. Graphite, regolith, dirt, okay, soil, Mars rocks, moon rocks, or aluminum. Aluminum's not that good, but you know, regolith tends to work on solar particles, but there's the problem. Galactic cosmic rays, for aluminum and polyethylene and dirt, they don't protect you. It goes right through them. So even if we dig down into Mars, you'd have to dig really deep into Mars to protect yourself from galactic cosmic rays. So we have no GCR radiation protection for astronauts in deep space or on Mars. And the problem are these guys, energetic cosmic rays. You're probably wondering what they are, and they are stripped nuclei. Because when we bust atoms up, we get muons and pions and all these parts of matter that spin around and spin out of existence. And there's the problem. In this model, the alpha particle. And that's what it is. It's 5 nucleons. Or beta particles, or gamma rays, neutrons, galactic cosmic rays. Nitrogen would then have 25,856 mass electrons. Oxygen would have something close to 29,600 mass electrons. And when something from outer space comes in with no shielding at 43 to 99% of the speed of light at 1,000,000 megavolts to 10 gigavolts and hits that stuff, you get a lot of particles. That's what I think is the mechanism for cosmic ray secondary radiation. The Ulysses spacecraft has found that that's increasing 20%. And they go through Earth, they go through everything. And at Mars, no better. Why? Carbon dioxide atmosphere, same problem. And they already know the cosmic ray environment is going to be based on depth. This is an altitude map of the globe. Hellas is that dark blue dot on the left, and the Tharsis Shield are the very high points on the right. So the physical characteristics and available resources. Well, Mars is a toxic planet. The mechanical, chemical, and photochemical exposure of astronauts, habitats, and spacesuits from dirt, atmosphere, solar, and stellar activity is significant. Solar radiation, methane, ozone, perchlorates, carbon dioxide, airborne dust, and UVB, pressure fatigue. Got a lot of methane coming out of the rocks in the summer in these areas. Probably know why. I'll talk about it in a second. Here's Mars meteor. It's made from olivine, which reacts with water to form methane. So there's water on Mars, and there's olivine on Mars, and we get methane. I don't think it's microbes. I know people want to find life on Mars. I don't think it's going to be bacteria specifically. The atmosphere is mostly carbon dioxide. But what about the old panspermia ideas, that these meteorites have come and injected life into these planets in the form of fungi and stuff? That's very interesting, because they have found evidence of alien life in meteorites. And molds are interesting, because they inhale oxygen and create CO2 at a much higher rate than living organisms like us, mammals. So maybe that's what we have on Mars, not a bacterial life form, but a very aggressive fungal life form that we may have no protection against. Ozone's very high. Perchlorates are terrible on Mars. There's a huge carpet of them all over the planet. They blow in the dust. They block up the sodium iodine symporter on the thyroid. So you can't get salts out, you can't get iodine in, your thyroid doesn't work, blood can't get cleaned. Not good. So they can't enter the gas environment. And there's this material issue with radiation. So you won't be able to live on the surface. Most of the stuff is going to be robotic or very brief moments out on the surface. And you can't use a regolith for growing anything. I mean, you'll get germination, leaves, but no flowers. And that doesn't work with tomatoes and things like that, right? So we're going to have to be underground. Well, we can grow hydroponically. We don't do that. Problem is, you're going to need to bring a lot of stuff from Earth or recreate a lot of the mineral environment necessary for healthy plant growth to do it. So we got TRL-10 and propulsion and logistics and environmental support. We're getting there on habitat, solar radiation. We got a big 0 on galactic cosmic ray shielding. So a manned mission failure rate is 100%, no doubt. So the reality of a Martian mission in financial terms, I mean, I love this. Oh, yeah, let's jump on the roller coaster and go 1,000,000 miles an hour, right? They don't want us there. But seriously, this is a $20 trillion mission if it all goes flawlessly. That's if. That's a big if. And can we afford it? Well, no. Currently, there's a financial crisis of $21 trillion in debt on the books with an inevitable global $1 quadrillion derivative crisis looming in the next 1 to 3 years, maybe this year, maybe the end of this year. Government near bankrupt, printing money with no real value to keep assets afloat. Global trade and outsourcing to low-wage countries has reduced their overall wages and taxes to be able to pay for these missions. Businesses have gone overseas, lost jobs and subsequent tax revenues, preventing a real recovery. 1998, the Wall Street banks bailed out hedge fund long-term capital management to the tune of $1 billion. In 2008, the central banks bailed out the subprime Wall Street crisis. And in 2018, the IMF will have to issue SDRs, which are special drawing rights payments, to bail out those banks. But there's really no money there. So the stock market's off the rails. Bond market's about to crash. We have a huge environmental crisis going on with pollution and our health. There better be a damn good reason to go. And if I was in front of the president or the head of NASA, I'd say there's better be a damn good reason to go. So getting people to Mars safely. Not yet. We are working on it. Here I am at Caltech. Bulk metallic glass composite architecture is a group I'm working with. We like these glassy alloys. They're as elastic as polymers and stronger than steel and titanium. They also reduce spall. So this is a particle hitting a sheet, and you have this, see the spall in that 76 thing? That's the debris after the hit, hitting things inside the spacecraft. Astronauts, electronics, life support. So we developed a material that when it's hit by that stuff, it has a much wider angle of diffusion and smaller particles. So that decreases the impact of the issue. And then we started building it in bulk metallic composites, where we weld them together, take them to the Ames Research Center, the hypervelocity gun, hit them with a pellet at 7 to 10 miles per second. And not only does it trap it, it prevents it from getting into the spacecraft. And that's great. Oh man, we got the GCR thing solved. No, take that into testing and they create x-rays. So you can't x-ray your crew for 2.5 years. You could. Elon might want to. And it's a debris issue and damage we've already seen on the ISS radiators, windows. This is just a flake of paint that hit one of the Space Shuttle Orbiter windows. Until we get to this, where we can actually have our own electromagnetic field to repel GCRs, you know, we could use these high velocity ideas because it doesn't matter then because you're getting everything out of the way. But that's not where we are. So the conclusion is because of a lack of qualified space radiation shielding to protect biological life during a 160-plus day mission, it is safe to say for the next 10 years at least to deliver it and land on the surface for an extended period of time and return astronauts successfully to and from Mars is beyond our grasp. It is. It's a vastly different level of difficulty. There are solutions, however. One that hits me, there's an ethical issue with it, knowing that when you get exposed to this much radiation, you're going to get cancer and die in 10 or 20 years. There's just no way around it. You're going to get cataracts and all that stuff. If you go to any Gold's Gym, you're going to find 70-year-old guys totally buffed, beefed up, huge muscles, in shape, great shape. They're only going to live 20 years. That should be our astronaut corps. No, I'm not joking about this. Think about it. These guys will have the strength and stamina until they're degraded by radiation to start building the structures under the ground on the moon and on Mars. And they'll be happy to do it. They'll take one for the Gipper, you know? They'll get up there, they'll be the heroes, they'll be the explorers, they'll be the guys who are out there on the Conestoga wagons getting killed and frozen by the elements. They'll be the guys to get us set up. Then, maybe by that time we'll have some shielding, and the guys will get out there at a younger age to do stuff. But that could be a way to get it going even now. Older astronauts. Count on the loss rate, because over a long enough timeline, everybody's survival rate drops to 0, right? It's where you start the timeline. One of the things I'm working on is something that works with a discovery by a guy named David Hudson years ago, and I know David, and he's a chemist, and they worked with me to do it, is dielectric and diamagnetic repulsion, atomic size frame GCR shielding. As we know, when the sunspots go up, the GCR rates go down. When they go away, GCR rates go up. So Jones-Wright will just launch during those time periods where we at least have the most protection that reduces some risk. But when you take gold down to the ionic state and boil it in acid for 6 days, it forms cubes. But after 7 days, it forms sheets. Is the gold diatom a dimer? Is it a positive and negative type of gold? They talk about this in the old alchemy, the purest gold, the gold of the 1,000 mornings and all this stuff, right? And maybe that's what they saw, didn't know what it was, but it could be a special oppositely spinning atom of gold that deforms the sodium chloride crystal into these ribbon shapes. So I took it into thermographic analysis at the Beck building and the Keck building to get identical results. And the samples lost 200% of their starting weight. They were levitating inside the electromagnetic cup in the field, in the heater field. Oh, that's great, because if you go back to this, electromagnetic fields repel GCRs. Isn't that interesting? So I'm thinking, okay, took it in there. Here's the cycles. 1 through 3, it's starting to go. It's starting to change. This is under 900 degrees centigrade down to 0, back up unendingly under argon, until finally a pattern starts showing itself. Until later, it would do it every time. So I profoundly changed ionic gold into a new physical property ion of what we know as gold. And there it was in the cup. Took it into this superconducting quantum interference device, that's SQUID, and metallic gold, no diamagnetic signature at all, but the ionic gold did. Towards room temperature, it was starting to get stronger in its diamagnetic and dielectric fields. So what if we just painted our spaceships with this gold foil? If you've got an energetic field at the atomic level, when these things come in, is that field strong enough to make these things just repel away? You don't want to bother trying to capture it. You just want to reflect it. And a dielectric diamagnetic potential high enough might do that. So maybe that could be a solution. So we're investigating that right now. What's really interesting is this is totally hypothetical now. All these pre-Columbian art of gold astronauts and gold spaceships and gold flying ships, maybe that's something they were remembering about gold, but that's curious. Of course, they could have made it in gold because gold lasts, and they wanted these little trinkets to last. But maybe they were trying to remember something. Maybe the things they saw during their lifetime and their historical events were these things, these guys in golden suits. Maybe, don't know. An idea. But one thing is we could probably send robots up there. AI is getting pretty good. We can get them up there. We can operate only a little bit of a lag. Have a guy in a headset down here at a control station operating the robot in the structure, doing stuff in the experiments, driving around outside, flexing his robot muscles, doing your lightsaber tests. We're going to figure out a way to get up there, maybe with the old astronaut concept. And we will be on Mars. It's only a matter of time. We're a spacefaring species, not just a nation anymore. We're going to get there. We need to get there. For my very first presentation in front of these groups, we need a second home. We need a backup, because if something happens here to knock this thing down for a couple of centuries, need to be someplace to reseed. Because it's our legacy. We've always been exploring the frontier. Thank you.